Okay, welcome back to our lecture on induction. This is part two. And I just want to finish reiterating what we said last time. Let me draw a little line here. So we're talking about induction. We use the symbol L. L has to always be greater than 0. So that's true. Now imagine we've got these inductors here. The current is flowing from A to B both ways. However, in this situation, the current is increasing its magnitude, and over on this side, the current is decreasing its magnitude. So two things happen. If you're increasing your magnitude of current, your EMF that is generated through self-induction is going to cause an EMF to go from A to B. So we'll have it will look like a battery like this, okay? And opposing the current that's going through. And on this side, when we are declining our current, well, the Lenz's law forces a current to go this direction because the EMF wants to go and increase the current. So it's a Lenz's law thing, and you can get into the details of it if you want to think about that. But it's really self-inductance, and whether you're increasing or decreasing your current, it will fight. The EMF will fight that increase or decrease and send current either more into or less into as a result. Okay, so that's a very it's a very big thing, and of course we can flip it, right? We could have current going from B to A, and we could have current going from A to B and increasing and all those things, and then ask what the EMF is in those situations. So let's do an example. And essentially this is example 14.2 in the book, but I made a little bit of changes to it. So you can go if you want to. Of course, I think you should. Go to example 14.2. And let me just write out what we know about the situation. So we've got an EMF of 20 millivolts. We've got N is equal to 50 turns. And our I is increasing. So I, they don't really, let's just say it's linearly increasing. I of t goes from 0 to 0.5 amps. Okay. So, and it does that in a time is equal to 0.1 seconds. So we can do our so di of t dt, we can basically just go like this, delta I over delta t, and we'll get our 0.5 divided by 0.1, and then we're left with amps per second. And everybody knows that that ends up giving us a 5, right? So, cool. 5 amps per second is our DIDT. All right, so what do we want to know? We want to say, okay, A what is our self-inductance? So we have to do that equation. Let's rewrite it. So L is equal to our EMF, and we're going to take the absolute value of that, and we're going to divide by DI dt, and take the absolute value of that. Well, it's convenient because we have absolute values of both things. So we're going to take our 20 millivolts and divide that by the 5 amps per second. And of course, well, let's put our units on there. We need to have units. So that's going to give us henries, right? So our volts seconds per amp is a henry. And what is that going to leave us with? That's going to, 20 divided by 5 is 4. Milli means 10 to the minus 3. And Henry. So that is equal to our self-inductance of our inductor. Okay? Whatever that inductor happens to be designed of or made of, coiled wire, however it exists. Okay? Now, B, let's give ourselves a little more room here. That's too much room. There we go. With the current at 1 amp, what is the flux? So, well, why did I say wet when I wanted to write when? Interesting. It's too early in the morning. When current is 1 amp, what is the flux through each turn of the coil? And by flux, of course, we mean the magnetic flux, right? So we want to know what that magnetic flux is through each turn in the coil. Here's where we're going to go back. You can go back up the screen or whatever to look at our equation for flux. So this equation, right, you might want to write it down in all the different ways, right? So you could write it down as our inductance is equal to N times our magnetic flux divided by the current. However you want to think about it, but this is the basic equation, and then of course you're going to be solving for our flux, right? Our phi. So the phi of B, we want the magnetic flux. So we know what L is. We know what N is, right? We've got our N right here. And we know what the I is because we're saying that the current is 1 amp. So we're going to just put 1 amp here. And so we know everything about this. And now we can solve for our phi of B. And we're going to put our 4 times 10 to the minus 3 here. And put our 50 down here, and our current of 1 amp. So we're going to multiply this whole thing by 1 4/5, right? That's 4/5, and 4/5 is 8. Okay, now here is another thing that we really haven't discussed, so let's do it. Let's just do 4/5 times 10 to the minus 5, and we can say that that's 0.8 times 10 to the minus 5. What are the units? Okay, so the units of flux are Webers. Okay. Did we get into that at all? Let's talk about Webers just for a second, because I don't remember talking about that with you guys before. So we've got flux. Flux, magnetic flux, is equal to our magnetic field times the area. And of course, we're not taking derivatives. We're not doing any of that stuff, right? We could take the derivative and, it's a B dot A, which is B dot N hat times A, all right? Where the N is the normal of the area, which gives us our B, which could be B of T times A of T times the cosine of theta of T. All right, we could have that. Fine, good. But what I really want to do is talk about the units. So this thing's not going to provide us with any units. This one is going to provide us with meters squared. And this one provides us with Teslas. So when we're saying phi is in Webers, 1 Weber, and Weber is a Weber. It's named after some physicist. I don't know. But anyway, somebody was working on this, and we decided to honor them with this. And so 1 Weber is equal to 1 Tesla times 1 meter squared. So that is a Weber, and we just came up with our phi of B for the situation in the example. So, okay, so Webers are now part of our repertoire, and we can put those in every single time we have flux, a magnetic flux. Okay, it's magnetic flux that we're talking about. Okay, now usually we see solenoids, all right? We see cylindrical solenoids. And that's why the inductor is drawn like this, because if you were to look down, if you were to look at it from this point of view, you would see this thing with some current going in one side and current coming out the other side, right? And all you see are these coils. And who knows how long it is? Could be perfectly long or perfectly concentric and infinitely long, and you wouldn't know, right? If it was perfect. Hard to tell. But usually things aren't perfect and it looks a little bit like this, and the longer it is, the kind of more fuzzy, right? It is. Okay, so that's a long solenoid, or if you wanted to draw it like this, and you're gonna have to look down the length of it, right? So we've got maybe current going in this direction and coming out this direction. So, and we could be looking down the length of it. Okay. Who likes imperfections? Nobody. Me, I guess. I'm the only one. Okay, so we've got current going in here and coming out here. All right, so that would be our inductor. One is looking at it from one angle, one's looking at it from the other. Okay. So there could be all kinds of setups, right? You can have you could have something that is rectangular, right? And you just have a rectangular toroid, and looking at it edge on, you've got your current going in one side and coming out the other, okay? And that thing would look from the side something like this. And all along here, let's have some current come in on this one side here. So there's our current coming in. And current leaving on the other side. And then all it is filled with wires that are going all the way around this empty middle space, right? Empty middle space. Empty in here, right? Empty. And just wires, wires, wires. Okay, and then we've got current going in and current coming out. Okay, so what are these two things? This one is a cylindrical solenoid. And this one is a rectangular toroid. Okay, so put that in your hat, I guess. All right, so a rectangular toroid isn't very hard to describe mathematically, okay? So they're both fairly easy, okay? We're going to deal with this one first. I'm not sure how much we're going to get into rectangular toroids. I just don't remember. But I'm throwing it out there. So if we talk about it a whole bunch, then it'll be something that you'll want to know. If we don't, I think we'll probably be fine. But for whatever reason, I'm saying it isn't hard to describe mathematically, so I have a feeling we're going to do it. But like I said, I can't remember. I don't remember 1 year from the next. Okay, so cylindrical toroids, that's our, solenoid. The cylindrical solenoid, that's our topic. Okay, so let's get into, this is just an aside. Okay, so let's talk about our cylindrical solenoid. So we have done what the B field is in the middle. Okay, we've said the B field for a solenoid is mu naught Ni, right? And you guys have been pretty good about it. Oh, I'm so good with this random solenoid stuff. What are we talking about? We're talking about this B field that we're producing down the middle. That is our B field for our on the inside, okay? Okay. So what is N? N, of course, is our number of turns per unit length. And let's call this a unit length. And so then we can say this is our unit length here. And how many turns did we have in that length? We had N turns, right? So we take N, we divide by L, and that gives us our N. So let's put that in. So we now have mu naught big N over L times I on the inside. And we can then say, what is phi? So phi, our magnetic flux, is this B times A. So we've got our B. We're going to times by A. Everything's perpendicular, so we don't have to worry about the angle. And we're going to then say I'm going to put the A before the I. Why? Because the I might change. So when we go to take the derivative of this thing, all these things are going to be constants, and the I will be the thing that gets the derivative. So there we are. Now, this is per each turn of the solenoid. Okay? So per each turn of the solenoid. Okay? So that's our B field per each turn of the solenoid. All right. So we're going to get clever and use our new stuff. Okay, so this is our new equation, and I just wrote it up here for you guys, right? So you see that in big box here, right? All I'm doing is this equation, okay? So let's go back on down there. So I've rewritten that equation, and what is that going to do for us? Well, that means we can do this L equals N over I times phi. And of course, it's our magnetic. You don't want to forget that, because we've got two, right? We've got the electric field flux and the magnetic field flux. So, okay. Now let's plug in what those things are. All right, so let's plug it in. So this is going to go into here, okay? And it's not just this part I circled, it's the whole thing, right? That whole thing's going to go in there. So now we've got mu naught. We've got n times n. So I've got n squared. And I'm going to be dividing by L. I've got area. And I've got I. On top. And I've got I on the bottom. And so that's going to cancel. And I think that does it for us. Yeah. Good. Now, no, that's great. Okay, so let's rewrite it. I want to rewrite it. Mu naught n squared, and I'm going to put an L down here, and I've got my A here. That's what we're left with. Now, what happens if we take that A and multiply L by it? Okay? In order to multiply L by that, we got to double up on the bottom. Okay, that's fine. But let's relook at our solenoid. Okay, and if we relook at the solenoid and we go and we want to look from this point to this point, and we've got some length L and we've got some area that this thing subtends, what have we found? We have found the volume. So AL, the area times the length, is equal to the volume. So that's it. That's when we multiply A times L, we've got our volume. So we can go back to mu naught times n squared, because don't forget, n over big N over L. Big N over L is equal to little n, right? That's our turns per unit length. So we've got n, and we're going to then multiply by the volume. I'm not calling it a V. I'm always going to write volume. We don't see volume that often, so just stick a little VOL on there to keep it distinct from voltages or velocities or any of the other V things that are out there. Okay, so this is our, again, self-inductance for a solenoid. So now, to get the volume, you just need L, and you need your area. We need the number of turns per unit length. And of course, everyone knows mu naught. So it's a purely physical thing, right? This L is purely a physical geometry-based thing. All right, and that's our inductance. So great. We have some cool stuff. So yeah, I did not remember that we're going to get into our rectangular toroid at all, but we're going to do it. Let's do it now. So here's the rectangular toroid. If I didn't have two R's in it before, it needs it. So you can go back to past me and be upset. Okay, a rectangular toroid. All right, so what does that consist of? I showed it above as a straight line, basically a long box, but I probably did everyone a disservice because it really should be something like this. And we've got some radius R1 to this point. And we've got this is the center, right? And we'll have some segment, we're going to do some segment of this thing that we're going to call dr. And then to this point, we've got r. So that's r is our variable, right? That's our independent variable, right? All right. And of course, this height isn't going to change, so that's a constant. And R1 is a constant. That's the inner. And our outer. Of course, we have an outer to here. That's our R2. That's not going to change. All right. And then now all we have to do is figure out what this area is. Okay, this area that I've shaded in. Well, that's D area. And it's just the height. Oh, there we go. Height times our dr, right? So that's our area. And all we've done is bend the solenoid, okay, to make our integrals easier. And, I'm sorry, bend the toroid. And we've took the solenoid loops and we've made them rectangles. So we've bent it and made it rectangles. I should probably put that in there. Geometrical thing. Okay. So you can go and look at example 13.8, and that's what we're doing basically. And we're going to show that our b as a function of radius is equal to mu naught n I over 2 pi r. I don't know if we're going to show that. Here's what I'm saying. By we're going to show, what I'm going to say is it can be shown. How about that? This is our B field. All right. So we're going to start with our B field. We're going to get our flux. We're going to go from our flux, and so our B field's going to give us a flux. Then we're going to go through and use our flux and the equation n phi equals Li and get our inductance. Okay. So in the end, we're going to go from a known B field that, again, we could figure out that that's the B field if we really want to. Probably should have, like, last chapter or whatever, but just take my word for it. That's it. And we're going to move on. So that's our B field. We're going to get our flux, and then we're going to take this equation and get our inductance. All right, so those are the steps. Okay, so what is our flux? Our flux is our integral B dot dA, right? And it's easy. It's gonna make everything easy because I'm gonna have it set up so that our B field is completely perpendicular to our area, so we don't have to worry about an angle, right? We're gonna just be going all the way around the loop, and of course our B field, when you do this loop, our B field is going to be at this point. Okay, this is depending on our current direction, it's either into or out of the page. So I'm just going to draw B field out of the page, but it doesn't matter. Into or out of the page, we're going to take the same positives on this thing anyway, so it doesn't matter. Oh, I don't want blue. Okay, so what is this integral in reality? We're going to go from big R1 to big R2. And we've got our B of R. And we know what dA is. We've already figured that out. So we can put HdR. Cool. And now we can pull out a lot of stuff, right? We've got our mu naught Ni over 2 pi. All that stuff hangs out front. We've also got an H we can pull out front. I think that's it. And let's go from R1 to R2. And we've got dr over r. And everyone knows that's going to give us the natural log. So here's our mu naught Ni over 2 pi, don't forget the h, natural log of r. And we're going to evaluate that. This is the best part of having a little pad like this. We're going to evaluate it from R1 to R2. And that's equal to R phi. Okay. So let's come back down and actually write that. Write that out. Put it here. Phi is equal to mu naught. Should we move the h out? Put the little guys in front. Put the pawns out in front, right? Okay. Okay. So I'm going to slide us back over a little. All right. So there's our phi. And now we can do our n phi divided by I equals our L. This is easy peasy. Immediately we can see that the I is going to drop and our n is going to be squared. So our L is equal to mu naught h n squared. I goes away. We've got 2 pi on the bottom. I'm just checking my notes to make sure I got this all written correctly. Yeah. Yep. That's it. R2 over R1. which should be the case, right? R2 is larger and R1 is smaller, and L is always positive. So that leaves us with the inductance that we need. Okay. We've got a little bit more to cover. I'm going to do that, and then I think we're gonna leave it there for the weekend. I'm sorry, until tomorrow. So so let's just do a little bit more. And so what do we got? We've got power and energy. So let's start talking about power and energy. Because how is energy going through this thing? What are we getting power-wise? Well, first of all, everybody knows power is the amount of energy per time. All right, so we'll probably look at energy first, right? We'll figure out what this is, and then everybody knows what time is. Well, everybody thinks they know what time is, so we'll put time in and get our power. So let's do this. Energy. Usually we're talking about, when you do energy, you want to know about work, right? Or the energy density. So there's a few things that you want to know about. Energy, work, energy density. Why energy density? Because we're dealing with magnetism. So there's no monopoles, which means it's really the moving of charges that's creating our magnetism. So our energy stems from the moving of stuff that is on the opposite end of this electromagnetic theoretical situation. So we are going to sum up energy as an energy density. Let me put it a different way. We've got some inductor, okay? And we can store energy in it, or we can take out energy. Okay, so we can either store or take out energy. All right, from this thing, from this inductor. Mostly we just want to account for the energy. But where's that energy coming from? What is it? It's the energy of the B field. Okay, we are generating a B field, and we want to know what the energy is stored in that B field. The other thing is, we know these things as a function of their volumes, right? So if we know volumes and B fields, we can get energy densities. That might be a better way of thinking about it. So we can integrate, if let's say we have some energy density. Little u, okay, of B. We can integrate that du and get our total energy. Okay, so that's the point. We're going to integrate that over the volume. Let me change my integral around. I don't like this anymore. In the end, we want the total energy, big U, so we can integrate this little u over the volume. Okay? Good. That's a better way to put it. All right. So we're going to integrate this thing over the volume. Now, it's not all volume. It's not all volume of space. It's just the associated volume, right? So you can't do all of space. We're just going to do the inside of our coils. And we'll get the total energy. So let's find our magnetic energy density. And I'm trying to think. Okay, I think I want to write this first. So for a solenoid, our B is mu naught N I. Okay. The L, our inductance for a solenoid, is equal to mu naught N squared times the volume. Okay. Great. I'm not going to derive it. We're just going to start. We're going to start from. We're just going to start with this UB. I'm not sure if they call it UB in the. I like keeping the B field, which is the magnetic field. They might call the little sub B, they might call it an M for magnetism. I don't know. I'm going to say I've got this UB and it's B squared over 2 mu naught. Okay? All right. So we've got UB equals B squared over 2 mu naught. Now, all we have to do to get our U then is multiply by the volume. So I'm going to take my UB, my little UB, and multiply it by whatever volume I've got. Now, for a solenoid, since we're talking about solenoids, my volume is equal to my length times my area of this circle, right? So the area ends up being pi r squared. If you want to think of it that way, we're going to leave it at this. Okay, for now. So, fine. So let's insert these things. We've got our big U. We wrote down what B was here. So we've got B squared. So I've got mu naught squared, N squared, I squared. And I'm going to be dividing by 2 mu naught. And then I'm going to be multiplying by our volume. And our volume is LA. So what is that going to give us? A U equal to 1/2. Let's pull the 1/2 out. We've got mu naught N squared A, well, let's keep the L first. L times A. And then I'm lastly putting the thing that could change because it might be a function of time, right? Our I of 2 squared. All right. Well, what is a solenoid? A solenoid is mu naught n squared LA, right? Mu naught n squared LA. How about that? So our energy is equal to 1/2 our inductance times our current squared. And that is a nice result. That is what everybody likes to see. That's what makes physics fun. Okay. All right. It's like fine wine or whiskey or something. It's an acquired taste. Okay. So we've got our u equals 1/2 Li squared. Now, here's what we're gonna do. We're gonna do two things. We're gonna define our induced current. And instead of calling the induced current I, we're going to define induced current as little I, and it's a function of t. Okay, so we're going to do that. We're also going to say that our induced EMF is E. Okay, we can put an induced on there if we want. Maybe we should. Let's just leave a little induced on there. Okay, so we have defined our induced current as this and our induced EMF as this. That sounds fair. So our power is equal to IE, right? But we've changed things, and we're going to call it I of t times our induced. Right? So it looks a little bit different, but it's the same pi, right? It's the same PIE that we used to see, know, and love. And now we can insert our power equivalence, right? By putting in our E induced. So I'm going to write I of t times our E induced. But what is E induced? It's positive, so first of all, and then it's also the derivative. Should we go back up and see it? Just so you guys know that I'm not trying to pull a fast one. Where's our EMF? There it is. Okay, so our EMF is equal to our L times our derivative of I with respect to t. Okay, so let's go back down. Let's go back down there. All right, so here's our derivative of I with respect to t. Okay. fine. So far, so good. How do I want to write that? Let's write it a nice, easy way. Um, there's no really nice, easy way to put it. It's kind of, I think that's about as good as it gets, frankly. Let's leave the T off of I of T and try and write this in a nice way. And box it in so it looks more official. That's our power. Okay, what is this power that we're talking about? So this is power absorbed by the inductor. So it's either absorbed by the inductor or emanated, given up. By the inductor. Okay, power absorbed by the or emanated by the inductor. And that pretty much seals up our thing for today. I don't like writing the I next to the derivative of I, so here's how I'm going to write it. So not only are you multiplying by the derivative of the I, you're going to be multiplying by the I itself at a certain time, t equals t whatever, okay, at a certain time, okay? T equals a constant. So the power will be a function of time as well, right? That has to be a function of time as well. So I think this is a better way to write it right here. Just to keep the two i's separate. One you're taking the derivative of, one you're multiplying just what it is at that moment. And I think that's it. So let's kill this for now, and we'll see you tomorrow.